Hey everyone, so today we're going to be talking about the radical mechanism, and there are a couple things you need to know to really truly understand how to do this problem. So the first question is, what is the most stable place I can put my radical? What are my radical stabilities? And the most stable place that you can put your radical on an alkane is in the tertiary position. So this position is called the tertiary position because it has where the radical is. This is the carbon that the radical lies on. This carbon that the radical lies on has 3 carbons attached to it. So this is the tertiary position. This is followed by the secondary position, followed by the methyl position, followed by the primary position, then followed by the methyl position. This is secondary, this is primary, and this is the methyl position. All right, so the things over here are the most stable. The things over here to where the methyl is, these are least stable. And as we go closer to the left, we have a more stable radical. So this is radical stability. In addition to needing to know radical stability, oftentimes it's really nice to see how these bonding patterns happen in the radical mechanism. So radical mechanism patterns, I guess we can call this mechanism patterns. And these are just typically ways that we see radicals do their reactions. So one of the patterns is the formation. Or I guess let's start with breaking. We have the breaking of a bond. And so we have 2 atoms. There's a bond in between them. And again, every bond has 2 electrons in it. So we can break that bond. We use these single-headed arrows in order to show this. So this here is a single-headed arrow. Notice that, well, it only has one head. This is that head that we are referring to. Versus something like a double-headed arrow. This is not what we will use in mechanism and the radical mechanism, because in radical mechanisms we're only moving 1 electron, not 2. So we'll use the single-headed arrow. And what else we'll do is in breaking that bond, these arrows are telling us that these bonds are being broken. Where one of the electrons, this green arrow says one of those electrons are going to A. The blue arrow says one of those electrons are going to B. This is the way that we can break a bond in radical mechanism. We can also form a bond in radical mechanism. So I can take 2 radicals, again, let's just call them A and B. And I can form a bond by simply putting those electrons back together. So I push those electrons back together. This is the formation of a bond. Maybe I'll zoom back out. I zoomed in. I have a tendency of doing that. Lastly, we can have not just the breaking of bonds or the forming of bonds, but we can have it such the case where we have some radical. And that radical reacts with a non-radical. So this is a radical, it has the dot. This is a non-radical, it doesn't. We can react that non-radical with the radical such that they exchange roles in a sense. So what do I mean by that? Well, we can form a bond between A and B and have C, for example, with the radical alone by itself. In order to show this mechanism, what we'll do is we will form a bond. It's kind of like a mixture of the top and the bottom. This radical here is going to want to form a bond kind of like what we did up. Oh, that's not up here. What we did down here, forming a bond. But again, there's 2 electrons in every bond, and we've only done something with one of those electrons in that bond. So we need, oops, it spawned to my eraser. We need to show the other radical. And we need to show the other electron how it moves, and that will go to C. So notice that red arrow is the formation of that radical in C, and this orange these orange arrows show the formation of the AB bond. Okay, so this is radical stability and radical mechanism patterns. Now let us talk about how we can see these in practice. So we'll start with some example. Our example will be, let's say this is our example. Our example will be as follows. We have some organic structure, just some alkane. That alkane can react with Br2. It can react with H nu, which stands for light or heat. That triangle stands for heat. So this is be also written as light. This can also be written as heat. And what we'll do is we'll end up putting a bromine, one singular bromine on the most substituted carbon. We have to, and I should be even more specific, we have to exchange a hydrogen off of our most substituted carbon with a bromine. So let's first find our most substituted carbon. We have a primary, secondary. Oh, that's not secondary. That's a tertiary carbon. Tertiary carbon. These are all secondary, though, around this ring. They only have 2 carbons attached to them. So that tertiary is our most substituted carbon. But again, we have to exchange a hydrogen off of that carbon. So there's a hydrogen off of that tertiary carbon. We'll exchange that hydrogen with, maybe we can do it a different color, with a bromine. So this is what this mechanism is going to do. Now, we'll get to an example of that in a second. So now let's just get to the mechanism. So there's 3 steps in the mechanism. We have initiation. We have propagation. We have termination. These are the 3 steps in the mechanism. And they almost exactly mirror what we talked about earlier. So this first step here would be an initiation step where we take a non-radical and form 2 radicals. This here would be a propagation step where we make one radical a non-radical, and we make the non-radical a radical. And we have our termination step where we take 2 radicals and we form a non-radical. So let us do that down here. We can take bromine and we can basically split that bond. Now, why does this happen? Why is it bromine? Why aren't we just splitting a carbon-carbon bond, for example? We have all of these carbon-carbon bonds and this structure, for example. Why aren't we splitting those? Well, this reaction will always find the weakest bond to split. And in this case, the weakest bond is the bromine-bromine bond. So we will split this bromine-bromine bond. Again, we'll use these arrows that allow us to show that. And it doesn't matter how the arrows are drawn. If you want to draw them on 2 opposite sides like I've done here, you can. Oops, that eraser is a bit large. If you wanted to draw them like this, that's also fine. All we need to know is that the arrow starts at the bond and ends on the bromine. That's the most important piece. So we can show the formation of those 2 radicals. This is the initiation step. And quite frankly, it usually stays the same. Your teacher might also ask you to know the initiation step for some other radical, for example, Cl2, if you ever do that reaction, or N-bromosuccinimide, also known as NBS. But in this case, this is the initiation step most of the time for these reactions. The second step is propagation. Propagation step is when we take a radical, so the radical that we just formed, and we react it with a non-radical. So notice this was there's a non-radical and a radical, and that step we have our non-radical and our radical. So we should use these two things. Now propagation is now going to happen. Notice that we installed our bromine off of the tertiary carbon, but again, we had to exchange a hydrogen with that bromine. So we need to first draw in our hydrogen, and we'll do our propagation step off of the carbon-hydrogen bond and the bromine radical. So how would that look? Well, we should start by forming a bond. This allows us to form a bond between the bromine and that carbon, or the bromine and that hydrogen, excuse me. And we are going to take the other electron that's part of that bond, and we're going to push it on to the tertiary carbon. What does this give us? Well, this gives us BrH, and we'll use the pink color here to show the new bond that's formed, or HBr, oftentimes probably more often written that way, but both is fine. And this green arrow will be the formation of that radical. So we put a radical on that carbon. So this is that step. Oftentimes professors will ask you to also draw the propagation step that leads to the major product, because that's where most of the product is actually formed. So we just do the exact same thing. We take a radical, the radical we just formed. We can take a non-radical, particularly we will use Br2, so Br here. And we'll do the exact same thing. We'll start at this radical, form a bond, and push those electrons. Let me use a different color. Push those electrons here. So we break that bromine bond, use one of the bromines to form the bond between the radical and the bromine, the other electron in that bond to just form a Br. And what does this give us? Well, this gives us a bond to bromine, and it also gives us bromine with a radical on it. Finally, we have, well, I guess I should say this. Here is our major product. So we've shown the propagation step that leads to our major product. Finally, we have termination. Termination is when we take a radical, we take another radical, and we push them together to form a bond. So this is basically a bond formation step with two radicals. You can take Br and Br, for example, right? We formed Br, we formed another Br. We can take Br and Br, for example, and form a bond between them. Of course, you should also show the arrows that allow you to do this. So these arrows are sufficient. We form a bond between these two. We didn't have to choose Br. So oftentimes your teacher will only ask you to draw one of these termination steps, but we could draw more, right? We didn't have to just choose Br and Br, even though that's a pretty common choice among students. Another thing you could do is you could take, let's say, maybe this structure and another one of those molecules, because a lot of them will be made. Avogadro's numbers of them would be made. So we can take that structure and that structure and form a bond between them. Those two structures are the same. This structure, all I did was rotate. And we can form a bond between them. So this is the bond that I form between them, right? And that's another product that we could have made. We could have even made one other product. We didn't have to choose two of the same radicals. We could have chosen two different radicals. So we could have chosen the Br radical and this radical. And those could have also came together to form a bond, such that we get Br, this molecule, and a new bond between it and that molecule. So all three are potential termination steps that we could have gotten. So this is the complete mechanism for this particular reaction. Let's do one more mechanism just together to see if we understand. I encourage you to pause the video and to try this on your own. Let's see. Maybe we can do this one, Br2. And maybe we'll do heat this time. So pause the video and try this on your own. Okay, I hope you have tried this on your own. What we can do is we can first figure out, we can predict the product, figure out where we're going to put our Br. So we have a primary position, a secondary position, I don't know why I keep calling this secondary, a tertiary position, a primary position, a secondary position, and a primary position. Out of all these positions, the tertiary would be the one with the most substitution. In fact, I do want to edit this, or not edit this, but I guess we'll continue with this one, but I do want to show a counterexample. Let's say, what if we had something like this? Where would we do our, where we would add our bromine? In this case, we would have chosen the tertiary. The left case, we would choose the tertiary carbon. For this case, where would we which carbon would we choose? Well, we have the primary, the tertiary, the primary, the quaternary, the primary, and the primary. It's probably the case, you might be thinking that we're going to choose the quaternary carbon. But we can't choose the quaternary carbon because the quaternary carbon does not have a hydrogen that we can exchange. So remember, in order to do this reaction, we have to have, and I can highlight this, we have to have a hydrogen on the most substituted carbon, which means that every single time we're looking for these, we need to ensure that there is indeed a hydrogen on the most substituted carbon. Here there is. This quaternary carbon has a full octet. There is no hidden hydrogen. This does not exist. In fact, it would be very wrong to write, so do not write it. That is, we'll never ever do we'll never do a radical reaction off of a quaternary carbon. So anyways, in this case, we won't choose the quaternary carbon, we choose the tertiary carbon. But let us draw the product of this reaction. So we'll replace that hydrogen with a bromine. And that's it. That's all. for this particular reaction. If you were asked to draw it as a box problem, this is it. In terms of mechanism, we have 3 steps. Initiation. The initiation step, again, is where we take our weakest bond, our Br bond. This heat will break that bond. It's strong enough to break that bond. And we end up forming Br. The second step is propagation. We'll take that Br radical and we'll take the carbon radical and we'll, not the carbon radical, the carbon structure. We haven't formed the carbon radical yet. Our Br radical and our carbon structure. And we will make hydrobromic acid and a carbon radical. In order to do that, we'll draw that hydrogen that is on that most substituted carbon, form a bond between the radical and the carbon-hydrogen bond. And again, because this bond has 2 electrons in it, we're going to push the other electron onto that carbon. So whenever you start from a bond, you can check this from all of the notes that you might have taken thus far, we'll always break that double bond. Not the double bond, we'll always break that bond. We'll always have 2 arrows from that bond. From a radical, you only need 1. We're going to form a bond between bromine and our carbon structure. We won't form a bond between bromine and our carbon structure. Sorry, we'll form a bond between bromine and hydrogen. And our carbon structure is going to get a radical. And I guess we can keep consistent with our colors. It's the pink arrow that shows the formation of that radical. In the propagation step, you're oftentimes asked to draw the product, your major product, in the propagation step. So you should do that. We will take our radical that we just formed, Br2, and we'll do the exact same thing. We'll form our major product in doing so. So we can take this electron, 1 electron from our bond to form a bond, to form the carbon-bromine bond. And this other electron can go on to that bromine itself. In this case, we end up with a carbon-bromine bond and a bromine with an electron with the free radical. Finally, we formed our major product, EA. We formed our major product. So we can now talk about our final step, which is our termination step. Here I'll only draw, I'll draw them all. But oftentimes your teacher will only ask you to draw 1. So this is your termination step. You can take the exact opposite of the initiation step, which is everyone's favorite. You can take those 2 radicals and form a non-radical, and you do that by pushing these electrons back together, right? You can also take 2 other radicals, right? So I could have taken let's say Br radical and the carbon structure radical, and I form a bond between those 2. Or I could have taken those 2 structures, the 2 two carbon structures and formed a bond between them. And form a bond right in between them. These are how you would draw these products. Again, notice that our termination step forms our major product, and this here is our minor product. Okay, so I hope this was helpful. We'll do some more practice in recitation, as well as more practice in your homework and your quizzes. Be sure to look at those.